Have you ever tried to fix a problem and accidentally made it worse? You lower fuel prices to help people, and suddenly traffic explodes, pollution rises, and cities become unlivable. You build more power plants, and somehow energy problems still don't disappear. Why does this keep happening? Because most people don't see systems, they see isolated pieces. But in the real world, nothing exists in isolation. Every decision creates ripple effects. Every solution becomes part of a larger chain. If you want to understand energy, truly understand it, you need a different lens, a systems lens. Today, we're going to put on that lens. We're going to learn how to define systems, set boundaries, understand stakeholders, and most importantly, think about sustainability in a way that actually works, not just in theory, but in reality. Because the goal is not just to solve today's problems, the goal is to build a world where future generations can still make their own choices. So what is a system? A system is a group of components working together toward a common goal. Every system has a boundary. Inside the boundary, you have components and interactions. Outside the boundary, you have the environment. This sounds simple, but defining that boundary is one of the hardest decisions an engineer makes. Let's take a simple example. Imagine a coffee shop. Where does the system end? Is it just the walls of the cafe? Or does it include the farmers in Brazil growing the coffee beans? What about the transportation network that delivers those beans? If your boundary is too small, you miss critical details. If it's too large, your analysis becomes impossible. A good engineer chooses boundaries carefully. Now, anything that crosses that boundary is either an input or an output. Fuel is an input, electricity is an output, and sometimes, unfortunately, pollution is also an output. Understanding flows across boundaries is the foundation of systems thinking. Now let's move to a bigger concept, sustainability. In 1987, a definition changed the way we think about development. Sustainable development means meeting the needs of the present without compromising the ability of future generations to meet their own needs. This is not just an environmental idea, it's about balance. Every energy project must succeed in 3 dimensions. Environmental sustainability, it should not cause irreversible damage to nature. Economic sustainability, it must make financial sense. A system that only survives through continuous external support is fragile, not sustainable. And social sustainability. People must accept it. It must respect their health, culture, and way of life. This is often called the triple bottom line: profit, people, planet. A truly sustainable system balances all 3. Ignore one, and the system eventually fails. Now the question becomes, how do we move towards sustainability? The book introduces 4 strategies. First, behavioral change. Sometimes the simplest solution is not technological. Instead of increasing heating, you wear warmer clothes. Instead of wasting energy, you become more aware of your consumption. Second, improving end-use technology. The energy source stays the same, but efficiency improves. Double-glazed windows, efficient vehicles, better insulation. Less waste, same comfort. Third, improving conversion technology. This is deeper engineering. Replacing an old power plant boiler with a modern high-efficiency system. Same fuel, better output. Fourth, switching the energy source. Moving from coal to solar, from fossil fuels to cleaner alternatives. Each strategy has different costs, timelines, and impacts. And here's a subtle but powerful distinction: efficiency versus sufficiency. Efficiency means doing more with less, driving further with 1 liter of fuel. Sufficiency asks a different question: do you need to drive that much in the first place? Efficiency improves the system. Sufficiency questions the demand. Both matter. Now let's get a bit more technical. In energy systems, we often measure performance using something called heat rate. It tells us how much energy we consume to produce electricity. The key formula is efficiency equals 3412 divided by heat rate. Here, eta represents efficiency, a number between 0 and 1. Heat rate is the amount of heat energy in BTU required to produce 1 kilowatt-hour of electricity. Let's take an example. If a power plant uses 10,663 BTU to produce 1 kilowatt-hour of electricity, its efficiency is 3412 divided by 10,663, which equals approximately 0.32, or 32%. That means 68% of the energy is lost, usually as heat. A systems engineer doesn't just look at one component, they look at the entire chain, from fuel extraction to final output, and try to improve the overall efficiency. Now let's step back and look at the bigger picture through stories. Engineers often use stories to understand complex systems and risks. First, the Titanic. Imagine focusing on rearranging shares on a sinking ship. You optimize small details but ignore the iceberg. If our energy system is pushing the planet toward instability, improving small efficiencies alone may not be enough. Sometimes the direction itself must change. Second, the endless football match. The environment is not a static system, it's dynamic. You don't win once and relax, you constantly adapt to stay in a safe zone. The moment you stop paying attention, you lose ground. Third, the emergency landing. Transforming an energy system is like landing a plane in crisis. Move too fast and you risk collapse. Shutting down critical systems overnight can damage society. Move too slow and you run out of time. The challenge is balance. Careful, controlled, intelligent transition. So what did we learn? Systems have boundaries, and we choose where to draw them. Sustainability is not just environmental, it's economic and social as well. Engineering is not just about equations, it's about understanding relationships, consequences, and long-term impact. And most importantly, every decision in an energy system affects real people, their choices, their opportunities, and their future. When systems are designed well, they expand freedom. When they are designed poorly, they create constraints and unintended consequences. In the next episode, we will go deeper into one of the most powerful tools in energy engineering, demand-side management. We'll see how shifting demand can reshape entire systems and reduce costs dramatically. Until then, keep your systems vision sharp, because once you see the system, you can never unsee it.